all good. And I'll send it to you after the talk.
No problem.
Oh.
Okay, can you guys see this screen?
Yep, all good.
Okay. Yeah. So today I want to talk how we can augment humans by using the body as an input-output interface. So before go further, let's look at some of the history of human computer interfaces. So most of the early interfaces, if you look at most of the early interfaces, you can divide those interfaces into three main categories: body operated interfaces like our keyboards and mouse, and then body tracking interfaces like our motion tracking systems using OptiTrack systems, and then body worn interfaces like smart watches or wristbands, which you can control other computing devices by using your smartwatch or wristbands. However, after 2000, with the advancement of ubiquitous computing and human augmentation, these body-worn interfaces slowly converted into augmented human interfaces. So if you look at these augmented human interfaces, they have some qualities. So the first of all, they are integrated with our body. So they use our body as an input. So they sense our physiological parameters or biomechanical parameters and then our behavior parameters. So they use our body as an input, as well as it use our body as an output. Sometimes it's not even provide feedback to our body, but also they use our body as an output device. So the concept of this integration of computers into your body has been explained in this paper, which is, I think, Freud also a part of this work. You can read it in Kai 2020. And then in augmented human interfaces, they use these sensed information to create an implicit understanding about our body. So they create an implicit understanding about our body, mind, and behavior by using those physiological, biomechanical, or behavior parameters. And then they sort of use that implicit understanding to enhance our capabilities, or refine our capabilities, or even adapt new capabilities. So in my research, I want to develop interfaces in this particular region, in the middle of this section, that integrate with our body and then understand our mind, body, and behavior implicitly, and then use that understanding to enhance, refine, or adapt new capabilities. So when I start my research, I look at how we can easily integrate these computing devices into our body. So one of the easiest way to do this is using our clothes or everyday clothing accessories as a base to integrate these computers to our body. For example, we wear glasses, we wear clothes, we wear shoes, insoles, and sometimes we wear rings, and now we even wear earbuds. So can we use these everyday clothing accessories to integrate computing devices, and then can those devices have an implicit understanding about our body, mind, and behavior, and can they improve our capabilities? So thinking in that direction, in my PhD research, I started exploring on how we can use our foot as an information source, and then how we can use our shoes and insoles to create augmented human interfaces. So I started investigating on the potential of the foot for novel input-output interfaces. So before go further, let's look at a little bit of history of these foot interfaces. So do you know what's the world's first wearable computer is? So reportedly, the world's first wearable computer, considered as an instrumented shoe that has been used to control that has been used to communicate in a casino environment inconspicuously. So this was developed by two MIT researchers, Edward and Shannon, and then they used a toe-operated switch inside their shoe to communicate inconspicuously to identify solutions for a casino roulette problem. And so we can see that ease of integration and the discreteness can be the two main reasons that they used SHU to integrate these electronics in this scenario. And most importantly, they are always available. So, but although shoes has been used as wearable computers at the very early stage, but after that, most of the early foot interfaces they were using as a kind of foot operated interfaces, similar to a mouse device. So this was developed by Douglas Engelbart. So this has been used to control the cursor or cursor of a mouse by using a foot operated device. So I started looking at some of the early interfaces, early foot interfaces. So you can see most of them were either foot operated, foot tracking, or foot worn interfaces. However, after the advancement of ubiquitous computing, you can see those foot interfaces have also been developed into augmented foot interfaces. So we identified this new paradigm of foot interfaces as augmented foot interfaces, and they are self-contained foot-worn wire interfaces with sensing or output capabilities that extend human abilities. So we provided this definition for this new paradigm of foot interfaces, and then we started exploring how we can develop these interfaces. So one of the important thing to identify is some of the opportunities that our food provides to develop these interfaces. So first of all, we can develop these interfaces as immediate interfaces, because whenever we go outside, we wear some sort of footwear. Whenever we go to gym, or even sometimes when we are inside our homes, we wear some sort of footwear. So we can develop augmented foot interfaces as interfaces that available immediately, anywhere, anytime. And then they can be used as discrete interfaces. So this is the quality that Edward and Shannon used in their casino roulette application. So in this image, you can see our lower extremity is quite invisible. So you can use these interfaces as discrete interfaces. And most importantly, our foot, we can use our foot to sense a lot of biomechanical parameters, such as center of pressure, or gait parameters, such as our gait speed or steps time. And not only biomechanical parameters, we can use to sense non-verbal behavior parameters, such as we can use augmented foot interfaces to sense our involuntary foot gestures. And then foot is consisted of a high sensitive nerve receptor. So it has a very highly dense with high sensitive nerve receptors. So we can use these nerve receptors to provide a subtle but efficient feedback to our foot. And also foot is we can use these interfaces as multi-purpose interfaces, because again we wear shoes always, anywhere, anytime, and then we can use those interfaces to sense contextual parameters, behavior parameters, as well as our physiological and biomechanical parameters. So by using these opportunities, I started developing these foot interfaces. So in coming slides, I will explain how I developed these interfaces. So first of all, let's start by looking at this input-output interface, which we named as gym soles. So we used this interface to improve squats and deadlifts by providing the feedback of the providing the feedback of our center of pressure, one of the most important biomechanical parameter of our body. So let's look at the concept behind this work. So when we perform exercises like full body exercises like squats and deadlifts, our upper body posture changes. However, our weight and all the impact forces are going through our foot. So whenever we change our upper body posture, these changes should be reflected in our pressure profile as well. So if we do some sort of an incorrect body posture when we perform these exercises, that also should be reflected by in this pressure profile. So we use this simple concept, simple idea to develop this gym soles interface where we can identify the pressure changes, and we can provide the feedback about these pressure changes. So the specific research question that we answer is, can we improve exercises such as squats and deadlifts while only providing the feedback about of our plant pressure profile. So we interviewed a bunch of trainers. So according to them, they use center of pressure as a reference point when they explain these exercise to their trainees. For example, they would instruct like, you should squat in a way that you feel your weight or the center of pressure at your heel area. However, the center of pressure is not something that you can feel. It's not something that you can internalize. So in this interface, what we wanted to do was we wanted to provide some sort of a feeling about the center of pressure to the user's body. So we started developing our prototype. So let's look at this video.
We present GymSoles, a system which assists users to improve squats and deadlifts by solely visualizing the user's center of pressure. The correct execution of exercises such as squats and deadlifts is essential to prevent bodily injuries. Existing solutions either rely on expensive motion tracking or multiple inertial measurement units-based systems. These systems are considered impractical, requiring extensive setups such as individual calibrations. This paper, therefore, introduces a proof-of-concept prototype, GymSoles, an insole system that provides feedback.
So I'm going to stop a little bit here. So you can see, so this is a interface that we developed. So first of all, I think the sound and the video is okay, right? Can you guys give me a thumbs up if it is okay, the sound and the video, because we have some more videos coming.
Yep, the sound's working fine.
Okay, great. Yeah. So in this interface, we had two systems. So one is sensing your pressure profile, and then it calculates the center of pressure by using the pressure profile. And then we had a shoe which had 8 vibrotactile motors attached to the side wall of this shoe. And then imagine that your center of pressure is somewhere here, and these set of motors will start vibrates. And then since the center of pressure is closer to these two motors, these two motors will vibrate in a higher intensity compared to these two motors. So in that way, users can feel where their center of pressure is, and then they can improve their posture according to that feedback.
On the center of pressure at the feet to assist users with maintaining correct body posture while performing squats and deadlifts. We evaluated GymSoles with 13 users in 3 conditions. No feedback. Vibrotactile feedback. And visual feedback. Results show that visualizing only the center.
So these are some of the results that we've taken. So this is the result of center of pressure profile. So you can see we considered a trainer's pressure profiles as the ground truth or the gold standard. So these are the center of pressure profile of the trainers, and then these are the results for the participants. And when they do not have any feedback about the center of pressure, they are significantly different to the trainer's pressure profile. However, whenever they are having the feedback of center of pressure, either as vibrotactile or as visual, they have improved their center of pressure profile significantly, and it's similar to the trainer's pressure profiles.
Center of pressure contributes to a significantly corrected body posture. Novice users were able to execute these exercises similar to that of an expert trainer.
We published this work in CHI 2019. So we also looked at whether they have developed their posture as well by only reacting to the center of pressure feedback. And then we collected the knee angle to hip angle ratio by using the motion tracking system that we use. And then you can see when they haven't any feedback, their profile is significantly different to the trainer's pressure profile. So this is the profiles for beginner participants. And then whenever they have either vibration or visual feedback of center of pressure, they have significantly improved their posture, and then it's similar to the trainer's pressure profile, trainer's posture profile rather. So we didn't stop there. So we wanted to improve this interface. So because our first interface is not wearable at all, so we instead of using a vibrotactile shoe, we converted our system into a vibrotactile insole, and then the feedback of the center of pressure directly provide to the sole of your foot, which is more sensitive than the side of your foot. And then the visual feedback we improved to a Google Glass. So then now we used this paracentric vision of the Google Glass to provide the visual feedback of the center of pressure. So in that way, users really not occlude the background vision, because now they can see the center of pressure visual feedback by using the paracentric vision. And then we published this work in Petra 2021, where we won the Best Student Paper Award. So let's look at how we developed this GymSoles++.
We present GymSoles++, an insole-based system to improve the body posture when performing squats and deadlifts. We developed a flexible wearable insole with 8 vibrotactile motors that provides haptic feedback on the center of pressure of the body. A custom PCB with 8 motor drivers and multiplexers was developed to control the vibrotactile motors. Additionally, we developed a visual feedback system by using Google Glasses. Our previous work has shown that visualizing hidden information on the center of pressure can assist users in maintaining a correct body posture when performing squats and deadlifts. We present gym.
So we were invited to demonstrate this work in Global Grad Show 2019. So a lot of people experienced this interface in that exhibition. So let's look at where this interface lies in this diagram. For example, so this interface is integrated with the body, so it sends the our biomechanical parameters, our pressure profile, and then it creates an implicit understanding about our center of pressure. And then finally, it uses the understanding of center of pressure to improve our posture. So we can use that interface to improve our posture by having the understanding of our center of pressure profile. So we can say that this interface lies in the intersection of these 3 qualities. So next, let's look at how we develop an input augmented foot interface where we use this interface to detect acute stress by looking at the pressure, our foot motion and pressure profile. So the specific, so the concept behind this is very simple. So we use a body language to identify our emotions. For example, one of the most popular body language that we use is our facial expressions. So we use facial expressions to detect our emotions. However, facial expressions is not the only body language that we can use. There are a lot of body gestures that we can use to detect our emotions. And then sometimes, according to psychologists and according to some of the people who use these things in daily basis, for example, like a person like Joe Navarro, who is a former FBI agent and a psychiatrist. So they say sometimes you can use body gestures even to detect deception. So body gestures in some certain scenarios, body gestures can be more powerful than facial expressions to detect emotions. So in this particular research, we wanted to develop a system where we use foot pressure and motion characteristic to detect acute stress and relaxation by using the involuntary foot movements and posture characteristics. So let's look at this video to see how we develop this interface.
Acute stress naturally occurs in our daily life. Episodic occurring of acute stress can cause a variety of negative symptoms, such as sleeping disorders, and may even result in chronic test. We propose using a pair of smart shoes to discriminate acute stress from relaxation by using a pressure-sensitive insole and an IMU. In a laboratory study, we induced acute stress for participants. Afterwards, we made them relax. We observed that acute stress resulted in an increased forefoot pressure, a shift of center of pressure towards the front, and a different foot-leg posture. Some users also demonstrated a nervous foot tapping while being stressed. Over time, the average electrodermal activity raised when the user was set under acute stress. In a relaxation task, the electrodermal activity dropped again. We developed several machine learning models that are capable of detecting both stress and relaxation to construct the validity of stress foot. We achieved reasonable accuracy rates for these 4 foot characteristics. To also demonstrate external validity, we conducted an in-the-wild study with 10 participants, performing their usual everyday office tasks over a working day. Our models demonstrated substantial robustness. To sense stress with our technique, we can upgrade any existing smart shoe or smart socks. Also, other form factors are feasible, such as a small sensor tag, or utilizing an existing pressure floor. For more information, please refer to our paper.
So you can see this is this work we published in Sensors Journal. So you can see in this work we conducted a series of studies to collect data and then to develop the model, and then we sort of test the generalizability of that model, and then we use the features of this pressure and motion characteristic to develop models that can detect stress and relaxation during sedentary tasks. So for example, the center of pressure, this is how center of pressure detect stress and relaxation. And then these are some of the other models that we developed using multiple features. And then later we also validated the external validity of these models by conducting an in-the-wild study. So these are the self-rated stress level for some of the participants, and then the model-derived stress levels. So you can see there's a very high they are very significantly correlated between each other. So our models can detect stress and relaxation by using these posture and motion characteristics. So in that work, we basically developed the model, and then next we wanted to see how we can integrate these models to our body, so we can create some sort of an implicit understanding about our stress during sedentary tasks. And then when we did our previous study, we identified that even a single IMU-based model can detect stress with an 86% of accuracy. And then if we can develop a small sensor tag, and then we can, if we can attach it to our shoe, we can create any shoe into an AFI, which can detect acute stress. So we created this sensor tag, and then we used it to attach into any shoe. And then in sedentary tasks, we started providing an awareness about the stress level to the users, and we even developed an interface where they can use this stress awareness to customize interventions. So they can they can create their own interventions, and they can program intervention routines. So the interface can interrupt them, and interface can ask them to change their behavior, and then in that way they can manage their stress. So we published this work in Mobile HCI, and then we won the Honorable Mention Award. So let's look at how we developed this stress shoe interface.
According to the World Health Organization, work-related stress is considered one of the most common health problems. Self-stress tracking at work is an essential aspect of stress management and is often the first step to improving mental health and personal well-being. Although there are many methods to track stress, systems for managing stress is yet to be explored. As a solution, we present Stress Shoe, a DIY toolkit for just-in-time personalized stress interventions for office workers performing sedentary tasks. We adapted a method to track stress, based on foot posture and motion characteristics, by using an off-the-shelf IMU sensor tag, connected with a companion mobile app. A focus group study and a pilot study informed the mobile interface design for stress tracking and personalized stress interventions. After connecting, the sensor needs to be calibrated. Then users can select the stress level and the logic of the condition to trigger an intervention. Finally, interventions can be selected. Users also can define interventions to control the sitting time. It also provides the option to connect with the IFTTT platform, enabling users to create many custom interventions. Moreover, for self-stress awareness, a visualization of daily stress log is also provided. To demonstrate the benefits of our system, we evaluated StressShoe with 10 users over 4 weeks. They were provided an IMU with 4 enclosures, which enables attaching the IMU to shoe in different ways. Users created personalized interventions and found that StressShoe is easy to use and helped them reflect on their daily stressful experiences. Some of the example applications they created are changing wallpaper to control the ambient environment, turning on relaxing music to create distractions,
does it make you dance when you're drunk with your friends at a party? What's your favorite song? Does it make you smile? Do you think of me? When you're...
Setting reminders for new routines like having a coffee break, or notifications for self-motivation. Users found that setting reminders for new routines are one of their most preferred intervention methods. For more information, please refer to our paper.
So let's look at where these stress shoe and stress foot work lies in this diagram. So it's certainly is integrated with the body. So it sends our involuntary foot gestures, and then it creates an implicit understanding about our stress. And then in stress shoe, what we did was we use this understanding to create new routines to manage their stress. So users can get new routines, new instructions whenever they are stressed. They can use those instructions to change their routine, change their behavior. In that way, they can sort of improve their the mental stability. So they can improve their stress management by using this interface. So I think this device is also lies in this region of this diagram. And then finally, I wanted to talk about this output interface, which is a Tickle Food. Recently, we published this work in Tokai journal. So in this work, we want to develop a novel foot tickling mechanism that can evoke laughter. So the concept of this work is very simple. So there are 2 types of tickling. One is nismesis, which does not evoke laughter, but it's self-inducible. So whenever we lightly touch our hand, we feel a sort of itching-like sensation or feel some giggles. So this is nismesis, but it does not really evoke laughter. And there's another type of tickling, which we call a garglesis tickling, that evoke laughter. And I'm sure many of us have experienced this at some point in our life, but it's not self-inducible. And most of the times it is interpersonal. So we need someone else to tickle us to evoke laughter. However, in 1999, Harris and Christenfield demonstrated that if you can really imitate the human tickling by using a machine, even a machine can tickle to evoke laughter. So suddenly the tickle not only interpersonal, it's also a reflection for a heavier tickling stimulation. So then people started develop tickling artifacts. So some use wrist, cheek, arm, even foot soles to develop these tickling interfaces. But most of these tickling interfaces create nismesis tickling, not garglesis tickling, and most of them haven't rigorously evaluated whether they can elicit laughter. So we wanted to develop an interface that can evoke laughter. And then when we look at the research behind tickling, according to the research, especially Charles Darwin had done a lot of research about tickling. So according to them, feet can be a good body location to tickle people, because foot has high concentration of highly sensitive nerve receptors. So we started developing a novel foot tickling mechanism to evoke laughter. So let's look at this short video to see how we develop this interface.
We present Tickle Foot, a novel foot tickling mechanism that can evoke laughter, by creating tickling sensations along the sole of the foot, utilizing magnet-driven brushes. At first, we developed an actuator that can drive brushes mounted on magnets. Then we conducted 2 studies investigating the most ticklish locations and stimulation patterns that provide tickling sensations to evoke laughter. We selected the pattern with a significant self-rated ticklishness. In a follow-up study with a new set of participants, we confirmed that the identified stimulations could evoke laughter. Finally, we embed our actuators into a flexible insole, demonstrating the potential of a wearable tickling insole. Participants' feedback implied that Ticklefoot would be useful in playful interactions connected with fun and laughter, such as remote interactions between loved ones. Eliciting mirthful reactions for entertainment. By changing the end effector, the device can also be used as a foot massager for relaxing, or even for releasing stress. For more information, please refer to our paper.
Yeah, so after developing this tickling artifact and then identifying the parameters that can evoke laughter, so then we explored how we can sort of evoke emotions as well by using this interface. So we conducted a study and then we identified while participants were experiencing this interface, their skin conductance level was rise. So that their skin conductance level was high, as well as we saw that they have a higher number of skin conductance peaks, which is an indication of they have some sort of an emotional arousal by experiencing this device. And then we also asked them to self-rate their arousal, valence and stress, and then most of the participants rated that they have been in a higher arousal and then they have experienced a higher valence while they experiencing this device, and then their stress level was a little bit lower. And then the behavior scale also showed that they, on average, they were either laughing or smiling while having the experience of this tickling interface. And so recently a new scientist did an article about this work, and then we identified that the findings of this emotional exploration was very pretty much interested for a lot of psychologists and neuroscientists, and they want to use this device in their research. Especially they think that they can identify the predictive coding of the brain by using such an interface. So we are looking forward to work with them in future. And then let's look at where this tickle foot interface lies in this diagram. So it's basically, it looks like it's only stimulating our soul, but if you look at the results of emotional exploration and the behavior, it's evoke laughter. So, and as well as it's sort of increasing the skin conductance level. So in that perspective, it's also use our body as an output interface, because it's not only simply providing some sort of feedback to our body, but also it's sort of evoking laughter, as well as it's also inducing some sort of emotional response as well. So in future, we want to we want to push this interface into this region by providing some sort of an implicit understanding. Maybe we can provide some sort of understanding about the stress level or the emotion of the users So the interface can identify what is the stress level or what's the emotion, and according to that it can react. And then maybe we can even use to increase some sort of capabilities by using this device. So that's something that we want to work with some of the neuroscientists and psychologists in future. So in my first work, I explained how we used shoes and insoles to develop augmented human interfaces. And then let's look at how we can use clothes to develop augmented human interfaces. So this work I did with some of my colleagues in Augmented Human Lab. So we published this work in CHI 2020. We developed an output interface to recreate human sensation, to provide a feeling of human sensation, human touch to users. So let's look at how we develop this interface.
We present a wearable forearm augmentation that enables the recreation of natural touch sensation by applying shear forces onto the skin. Our approach consists of lightweight stretchable plasters arranged in a matrix. Our design is informed by 4 different studies. Our matrix arrangement enables the perception of touches, for instance, feeling one's wrist being grabbed or the arm being stroked. We have also preliminarily evaluated 2 potential use cases. We present a wearable for.
So if you look at this work, this work also lies only in this region because it provides some sort of a feedback so they can feel the human touch sensation. But then we wanted to push this work into this region. So we developed, we connected this interface with a display, so they can so the users can create a digital art jamming session. So they can create digital art by collaborating with each other. So let's look at how we combine this interface to a digital art jamming session, and then how we push this interface into augmented human interface. You can see there are two users, and then both of them were wearing these interfaces, and then while they're doing the art jamming, they communicate between each other by using this interface, and then one person can feel the movements of the other person, and then according to that they can kind of create a better art jamming task by using this interface. Then we even conducted a study to understand how people can use this interface in art jamming. Yeah, so yeah. So in the first interface, we were integrated it with our body, and then it provides the human touch sensation to the body, and then we sort of sense the hand movements, and then we provided understanding about the movements to the interface, and then by using that understanding, we sort of try to enhance the ability of art jamming, or designing art by communicating with the other person, and then they can sort of improve their ability of creating art by taking the by feeling how other person is doing that. So you can see in our work, so at the beginning we created foot interfaces, and then we kind of used clothes to develop augmented human interfaces, and then in future we wanted to see how we can kind of connect these augmented human interfaces together, and how these several augmented human interfaces can connect it together, and then how they can improve our capabilities, how they can create an understanding about ourselves, and then how they can help us to improve our capabilities. So we gave the starting point for this idea by in GymSource plus plus. We connected GymSource with the mobile with the Google Glass, and then kind of explored how we can use this combined system to improve our posture when we perform squats and deadlifts. And then in future, by connecting all these augmented human interfaces, we want to give a rise to a discrete companion which identifies our physiological biological parameters, and then provides an implicit understanding about our body, and then uh, and then interfaces that can improve our capabilities. For example, at the moment we use our mobile phone as our explicit companion, but what if we connect all these augmented human interfaces together, and then we can, and what if we can give power to a discrete companion who understand our mind, body, and behavior implicitly, and can use that understanding to improve or extend our capabilities. So let's look at some of the takeaway points of this research. So augmented human interfaces are compute interfaces that integrated with our human body, and then they creates an implicit understanding about our human body, and then we can use that understanding to extend our human capabilities. So we utilized everyday clothing accessories to integrate augmented humans with the human body. So at the beginning, we uses shoes and insoles to develop these foot interfaces, and then later we started using on our clothes to develop these augmented human interfaces. And they could be used as our discrete companions that understand our mind, body, and behavior implicitly. And then finally, we think they will be beneficial to enhance our abilities to learn new skills like we did in GymSource, and then even we can use them for empathy, like we did in Jamify. Thank you so much. So that's all for today. So now I think it's the time for questions. So
Thank you very much, Don. Yeah, like you said, yeah. Does anybody have any questions? By the way, yeah, that was excellent. I really enjoyed that. Yep. Any questions from the audience? No. Oh wait, we got one in the chat, I think.
okay.
Floyd said, "Did you apply for any thesis awards?"
Yes, I think recently I got the ABI, I mean, University of Auckland Dean's List, and then department, ABI department, our Auckland Bioengineering Institute Best Thesis Award, and then I actually applied for the ACM Doctoral Thesis Award.
And have you heard back from them at all?
No, not yet.
No, not yet. Well,
Not
best of luck with that. I think if you get that, that would be well deserved, because this very, very amazing line of work that you did during your PhD. So all the foot interfaces, that was your PhD work, right?
Yes. Yeah. Foot interfaces are all my foot interfaces are my PhD work. Yes.
What about what was it called? Is it Touch Me Gently?
Touch
The
Me Gently, I did it with one of my colleagues.
Yeah,
So it's a part of his PhD actually. But I helped him to kind of develop the concept. And yeah.
awesome. Um, well, yeah, since we've gotten our immediate questions right now, I do have a few. First question was, so you were saying that you're with future work. Oh, by the way, so your interest in looking at like the body and technology for input and output, very similar to what I'm doing. I'm essentially doing like input output technologies for human physiological feedback loops. So we've got like a very common, I guess, like research line going on. And so you were talking about how you wanted to I guess like translate what you've learned from things like gym soul and ticklefoot, and try to look at it as like a input output sort of thing to create implicit understanding and also enhance human capabilities going forward. And I was wondering, like, have you thought of putting ticklefoot and like the stress foot, the stress soul together, so like the tickle foot is actually like I guess like an intervention
Yes.
for like like one of the interventions for stress foot or whatever it's called.
Yeah, definitely. Yeah, that's a good feedback, and we also suggested a similar idea in our paper as well. But when we consulted some of the psychologists and neuroscientists, they had some other ideas as well, because sometimes um, uh, the tickling is enjoyable according to the situation as well. So we might want to do like further studies on how we whether we want to really do tickling when people stress. uh, that's we need to do further studies in that direction as well, how people will react. But according to some participants, actually they were liked to get this feeling, to create some sort of distractions. So some of the one participant actually, she mentioned that she could use this to create some sort of distractions whenever they feel bored or whenever they feel stress. So I would say, using the interface to create distractions when users are in stress, need further explorations to see how this really affect to their experience, because some people might not like it.
Yeah, yeah, that's yeah, makes sense. Which also like takes me on to my second question, which is like, yeah, but did you do much, I guess like interviewing with the participants? I noticed most of like your the analysis that you showed in the results were like quantitative stuff, but did you do much like asking the user like what the experience was like and stuff like that?
Yes, actually, the application, we derived like several applications for this tickling interface. So those applications were derived by sort of analyzing the comments and feedback of the users. So then we asked them to sort of explain what they felt, and some of them were telling that it reminds some of the memories that even it reminds some of the childhood memories that they had, uh, like when parents tickling their food. So those memories came to their mind, and then some people were saying that this could be used for to elicit mirthful reactions. For example, like maybe you have seen that when we look at comedy movies or comedy dramas, they in background they have this laughing sound. So laughing is, they create this laughing sound to make you laugh actually. So because it's sort of a trick that they use to make people laugh. So can we use tickling to do that? So that's how this using this device in 4D cinema idea came. And then some people kind of telling about that they sort of felt like a fish tickling their foot. So they were kind of relating this experience with previous memories that they had, previous experience that they had. So in that way, we thought that this might be useful for virtual reality and augmented reality, and even to provide therapies. That's how this massaging device came into our mind. So yes, we sort of ask participants to provide feedback, explain their experience with the device, and then all these ideas for applications came out of the participants.
Awesome. Okay, that makes more sense. I think that Crystal also has a question. Did you want to ask away, Crystal?
Yeah, hello, hi.
Right.
First of all, I just want to say thank you so much for a job well done on the presentation, and not only the presentation, but all the projects you did in your PhD. I'm very impressed. And so that I'm a new PhD student. So I guess one of my questions would be, what advice or what have you learned that you would give persons who are developing their systems and their prototypes based on what you have learned and lessons, things you might not want to do again, and things that you definitely would suggest persons to do to come away with a body of work that's as impactful as yours?
Yeah, that's a really hard question. I think one of the major things that I learned during my PhD is um, the failures are common, and then you should try to learn from your failures. So none of these things came overnight. For example, like Jim Souls, the very first time that I submitted it, it was rejected, and for very obvious reasons. I didn't see those reasons, but then by looking at the reviewers comments, uh, I really appreciate then those comments, and then I really uh, wanted to improve my system. I didn't sort of let it go. I valued those comments, and I understood my mistakes, and started developing my work. I would say like none of my work was accepted at the very beginning. Most of them were rejected, and then I got very good comments, and then according to those comments I developed. And then it's also important to sort of create your own vision as well in your PhD. And sometimes it doesn't come to your mind at the very beginning. It's very um, it's common. It's a common thing as a, because you're trying to be a good researcher, so you're also learning a lot of things. So um, at the beginning of your PhD, it seems like you don't know where really you want to go, and you don't really know what you are doing. But uh, it's important to the perseverance is very important. Although you are failing again and again, you have to keep thinking about your PhD. You have to keep thinking about your direction, and so although you're not, it's not seems like you're not going anywhere. It's important to keep your mind relaxed, and then perceive something consistently. So I think the consistent is very important. Even in my PhD work, I didn't really, although I helped other PhD students in their own PhD topics, I didn't really deviated from my augmented food interfaces. So I sort of developed so many work in that area. So in that way, I sort of able to create my own research vision. So I think uh, two things, like uh, whenever you fail, you shouldn't get upset about that, and you should try to you should honestly try to improve your work by taking the feedback of others. I have seen, if you really try to submit to these first year conferences, the feedback that you get from those reviewers are excellent almost all the time. So you have to take those comments seriously, and then you have to develop your work continuously, and then the perseverance is important. And then finally, try to think about a vision, try to create your own vision, uh, and that doesn't come overnight. Consistency is the most important thing. Thank you.
Thank you. I can only like emphasize what you said there. Just finishing my PhD. Yep, 100% what Don just said. I'm just being mindful of the time. I guess we'll have like time for maybe one more question. So Vahid is asking, have you investigated interface connecting to the nervous system? I would like to know that as well, because that's what I do. Vahid, did you want to add to that, or? Is that it?
So sorry, what's the question again?
Have you investigated interfaces connecting to the nervous system?
So,
Not
sorry,
yes.
I had another comment after that. Maybe, yeah.
Yeah.
The question was, I mean that it can be, maybe it can be used for more general interfaces, and what are the current challenges in this area if you have investigated it.
So you mean the challenges in augmented human interface?
No, I mean using nervous system feedback, triggering nervous system, or getting input from nervous system. I'm not really expert in it, but yeah. I mean, have you investigated any interfaces with nervous system?
So in my work, not really. I haven't really tried to kind of intervene the neurological signals of our body. I really haven't tried. One of the reason was like I wanted to develop something that wearable as well, so you can wear your device and then you do not need to attach any other high tech or advanced electrodes to your body, because sometimes people need some sort of knowledge as well to add those electrodes to certain locations. So that's why in my work I sort of always try to leverage these already available clothes and clothing accessories to develop these interfaces. But it's very interesting area, because right now I think there are new sensors are coming, like dry electrodes that you can sense the electrical signals of these neurons or the neuroreceptors and neuroreceptors, electrical signal of these neuroreceptors and the neurotransmitters. So if we can use these dry sensors, probably I want to try those sensors as well in future, and then explore how we can use these sensors in everyday clothing accessories, and then how we can use those signals to improve our capabilities. And I would say tickle foot, in a way, it's connected with your brain as well, because tickling is a very special sensation that only humans and primates has. And then that's one of the comments that a neuroscientist has provided to that article. So you can actually, by using tickling, you can actually identify some of the certain capabilities of our brain. So maybe in future, I want to explore, as I told you in this talk earlier, maybe tickle foot might be in a very low-hanging area that we can explore how we can integrate this system with our neurological system.
Yeah, thank you. Thank you very much.
Yeah, I would just like to add to that. Like, I would argue that tickle foot already maybe is a neural interface, or because the mechanoreceptors that detect the tickling sensation are neurons. So you're directly activating neurons. It kind of is a neural interface there.
Yes.
Yeah.
Yeah.
Okay. So yeah. Sorry. Yeah. What were you gonna say?
Yeah, it could be we haven't really explored in that direction yet, but according to the comments of the psychologists and neuroscientists, I think it could be used as a neural interface already, if we explore in that direction in future. Yeah.
Cool. Thank you. All right. So yeah, again, just being mindful of the time. So we've gone over time a bit. So I'd like to thank you once again, Don, for coming and giving your wonderful presentation to us. I've definitely learned a lot, and I'm really inspired to do a lot more like body integration systems now after watching that. Yeah, so everyone give Don a round of applause. Thank you very much.
Thank you again for inviting me to do this talk. Thank you so much.
Cheers.
Hayden and Floyd.